Okay, hi class. Today we're gonna come to section 7.3, the central limit theorems for sample proportions. So last time we did learn about sampling distributions, and that will help us to talk about central limit theorems in these sections. Okay, so in these sections, we're going to identify the conditions needed to apply the central limit theorem for proportions. We're going to use the central limit theorem for proportion to describe the sampling distribution of a sample portion and to find probability. Okay, so let's get into the next page. Okay, so we have central limit theorem for sample versions in this page. You're gonna have two pages for this. We're gonna use use central limit theorems to estimate the portions in a populations. And central limit theorems will tell us that if some basics conditions are met, the sampling distributions of the sample portion is close to the normal distribution. Okay. All right. And if we take a random sample from a population, and if the sample size is large, right, and the population size is much larger, then sampling distribution of the sample portions is approximately normal. Okay, and this normal distribution will have the mean. The mean of P with a standard deviations of the formulas is SE, the standard error. And I did introduce this form before, which is P square root of P times 1 minus P divided by N. So if you don't know the value of P, you can substitute the value of the proportion, sample proportions. If you don't know the value of population proportion, you can substitute the value of sample proportion. All right. For the condition of the central limit theorems, we have three conditions. First, sampling is random and independent. Secondly, we need a large samples. The sample size usually labeled N, is large enough that sample expect at least a 10 success and 10 failures. Right? So at least it is that you want to have 10 success. 10 people say yes and 10 people say no. Okay. So and it's certified for N time with sample proportion greater than or equal to 10, and also like it's certified for the sample size multiplied by the 1 minus sample proportion greater than or equal to 10. Yeah, so the third condition is big population. And if sampling is done without replacement, the population must be at least 10 times larger than sample size. So as I stated before, right? Okay. Okay, so now we're gonna talk about central limit theorems. We now label as CLT for sample oceans as a picture. So the picture show samplings distribution of sample portions for 10,000 samples of the size 10 drawn of population with p equal to 0.25. So note that these do not satisfy the conditions 2, right? They're not satisfy the condition 2 of the CLT. So look at the condition number 2, which is we need a large sample with a size that have at least 10 yes and 10 no, right? In here, the size was just 10, right? So it's not have enough. And the sample, so then the sample size is too small, and so then the distribution is not normal. And you see below here, right? It looks like a school to the right. Yep. So let's move to the next slides. The figures show the sampling distributions we had for 10,000 sample size with hundreds drawn, right? So this is with a size 100. And then still using the population portion is 0.25. And as you see that this one satisfy let me use this. This one satisfy the sample size conditions of CLT, and the shape of distribution approximate normal, and you see here. So then the standard errors can be found as 0.25 times with 0.75 and divided by n, which is hundreds in here. Yeah, and then it's going to be 0.0423. Yeah. So according to so these are examples about vegetarians. According to statisticbrain.com, we have like 59% of veterans are human, right? So that means it is population proportions. Okay, p equals that. And suppose a random samples find us so you did have sample size as big as find us. So this is good, right? And what is the approximate probability that the portion of females in our sample will be more than 63%? So let me highlight this. What is approximate probability that the portion of female in our samples will be more than 63%. Yeah. So in this case, we look like we are looking for the case as P, the probability of P when we have the small proportion is greater than 63%, something like that, right? Or 0. 0. Let's say so right 0.33, something like that, right? Yeah. So so we want to find that in these examples. So you can go ahead and pause my videos and then try to check the conditions of this to make sure it satisfy the three conditions that's for COT, right, over here. And we can apply the single limit theorem for these problems. Okay, so if you check now, we can go. You can go ahead and pause the can continue the videos. All right, so here, let's check the conditions. First, as you can see, we have this sample was random and independent, so that's satisfying. The second one, say large size, is that large enough? You can check with n times p. You know that p was 0.59, so n was 500. So you do like 500 times 0.59, and it is equal to 295, which is absolutely greater than or equal to 10. So that's good. And then in another way, you multiply with proportion of failure. So n times 1 minus p is 500 times 1 minus 0.59. That's give you 205, and also it's greater than or equal to 10. That's 35. We're not sure the total people like vegetarians in population, but we can assume that there's at least about 5,000 in the population, and because we know it should be like so many people, right? It's not only just 5,000; it could be more than that, but we can assume that it should be at least that. So that this is be okay. Okay, and so this all meant for the COT uh, essential limit theorems. So we're gonna say this sampling distribution will be approximately normal with the standard deviation is FE or standard errors, and you can substitute P in the formula with N in the formulas and calculate it to get 0.022. Yeah. So we have SERs, right? And we also have the uh, in this one, I'm just supposed to say mean. The mean is actually the p we equal to 0.59, right? Okay, because this normal is approximate as a normal, so we can use the mean as p is 0.59, and the standard deviation we're using the standard error is 0.022. So now you can using that to say you're going to use the non-distribution as 0.59 and comma 0.022. So one was the mean, one was um, the standard deviation. All right, so now next we just using StatGrunch as a technology to find um, the probability of getting the value larger than 0.3, right? So let me open the StatGrunch. Let me see, is this stuff on here? I can use. Longer than I thought. Open this. Actually, it should be here, but this. Okay, so I'm gonna use StatGrunch here. All right, open structure. So you can click on let me see. There's no over here. Calculators over here. Set and calculator, all right, and go to normal. And then you have to change the mean to be what's the mean? 0.59, right? Standard deviation now change to be 0.022. That's the standard error, right? And then we want to get a value larger than 0.63. So larger, you should remember larger is greater than, right? So 0.63, yeah. All right, compute. So you should get 0.345 1817 something over here, right? So that's gonna be the way to use StatCrunch and read it get as 0.0345 at 3 decimal place is a property of that the proportion of female in the sample will be more than 63%. So we done example number 1, right? And we can move to example number 2 about voting. So in a closely contested school board election, polling indicates that 50% of voters favor the bond, right? Favor the bond. And 50% again. So you can see the 50-50, right? And then suppose that a random sample of 80 voters select. So as you see in here, you have N is 80, right? We want to find the first one say we want to find the percentage of sample who expect to favor the bond. And we're gonna say does the central limit theorem apply, right? And next one is find the standard error for this sample portion. So keep in mind that if part 2 say no, then you will not find a standard error anymore. Okay. If so, what is approximate probability that the sample portion will fall within 2 standard error? Okay, 2 standard error of the population values. P equals 0.5. Okay, so you can go ahead and pause my videos to work on your own, and you can, when you're done, you can go ahead and keep going with continue with the videos. Okay, now I'm gonna move to the next slide. Yeah, so the first question say what percent of the sample group we expect to favor bond, right? So because we have taken random sample, we expect the sample portion to be about the same as the population proportion. So we expect 50% favor the bond, right? Okay, and we have a random sample with 80 people. So you check N and P is 40, right? And I mean 40 is greater than 10, so that's good, right? And you can also check the fellows way also. So both within 10, so this is large enough. All right. And as you know, the poll could be like a lot of voters, and so we can assume that there are more than 800 voters in the districts, right? So the population size is at least 10 times larger than the sample size. So then we can say, oh, the condition for COT are met. All right, so then we can find the standard deviation, standard errors, which is using the formula 0. P times 1 minus P divided by 80, which is n. So 0.5 times 0.5 divided by 80, and then it's square root, and you got 0.0559. Yeah, so because we apply a COT, right? So then we can use the normal models with the the means will be the the proportions, and the standard deviations now are going to be standard errors. So that's the reason why you have 0.5, 0.00559. And if you use a empirical rule, you can add, for into standard errors 0.5, it's going to be 95% of this. And if you like, you can also using technology to verify this. Let me show you. So it is 0.5, and standard error is 0.0559, right? Okay, so if you want to have greater than what's that? Greater within 2 standard error. So I think we have to use between here. Okay, so let's say mean was 0.5. Okay, so this is good. In between 0. In between 2 standard errors. So if you subtract, I mean the 0.059, right? You can say, I mean, here it's not clear, but you can use calculators to calculate that. We have to use calculators here. So say 0.5 minus 2 times with 0.059, 559, I mean. It's going to be 0.382. The second one is 0.5 plus this 2 times 0.0559, and you get 0.6118. Okay, so this one is 0.618, and the one before was 0.38842. Compute. All right, you're gonna have 0.954. So as you see, group apply for this, and it's gonna have 0.995% as the answer. 95%. All right. So that's gonna be it for this page. Let's move to the next one. Okay, so yep, here we go. The key ideas for COT is if the condition for COT are met, right? The probability that the sample portions will fall within 2 standard errors the portion value is 95% for this. Okay, so because you know that it was if CT met, then the distribution now can follow by the normal, so you can just using empirical rule in here to make it easier for the life. Dog owners as example number 3. Okay, so according to AVM as associations, we have 36.5% of American owned dog, right? And so suppose that we're gonna use 200 Americans, and then it would be surprising to find that 45% of sample own a dog. Okay, so why not? So basically right now, first we have to check if it is CLT. Then we're gonna check, you know, we're gonna converse for the people for the 45% there back to the Z-score, and if it is like, you know, less than -2 or greater than 2, is gonna be, you know, unusual. Okay, so I expect really to be that in between one standard deviation. Okay, so let's see. You can go ahead and pause my videos, and when you're done, go ahead and click continues. Okay, so now check if certified CLT, and as you see the way, I mean it's always gonna be random independent sample, so good. And you check NP and N times 1 minus P is gonna be greater than 10, so that's just large enough. And then you can go ahead and, you know, assume the portion is at least 10 times larger than sample. Yes. And then you can say the means in here will be 0.365. That's, yeah, because 36.5%, right? Yeah, 36.5%. Go to that. All right. So 36.5% can be put to that. And then the standard errors will be equal to 0.034 if you calculate by the formulas. All right, so now we can, using the mean plus with 2 standard deviation, you can either go back, you know, convert it to the z-score, or you can just, you know, adding 2 standard deviation and see if it is like, you know, it is cover the 45% or not. But as you see that this 0.43 3 can be round at 43.3%. So that is that means 45% is more than 2 standard errors for mean. So is unusual, and we can say would be surprising. So example 3 did the stop the section 7.3 here. So I will gonna see you in the next session later, and see you.